Open a Roman harbor block or the Pantheon S dome and you're not seeing a miracle. You're seeing a recipe that manages chemistry for the long game, Roman concrete. The headline contrast is brutal. Many modern concretes struggle against rebar corrosion and environmental attack within decades, while Roman marine blocks and mass masonry keep gaining strength in aggressive conditions. The key is not one secret ingredient, but a system. Volcanic ash pozzolana, reactive lime made hot, aggregate that works with the binder, and a structure that doesn't depend on buried steel. The result is a material that can self-heal microcracks and even grow new mineral glue when seawater or rain infiltrates. Let's walk the evidence chain. What the mix was, how the matrix forms, why cracks don't doom it, and where modern design diverged. Start with the powder chemistry. Roman builders prized volcanic materials, especially ash from the Bay of Naples, because glassy, silica, and alumina-rich particles react with lime to build a dense, durable binder. When quicklime is used hot, added while still highly reactive, it doesn't just dissolve politely. It forms lime clasts, bright, millimeter-scale inclusions that look like flaws until you see what they do later. These lime clasts are reservoirs of calcium that, upon contact with moisture through hairline cracks, partially dissolve and re-precipitate as calcite. In other words, cracks become pathways to fresh glue. The matrix stitches itself locally without a repair crew. Microscopy on Roman mortars shows those clasts rimmed with reaction products and microcrystalline bridges that cross tiny gaps. The same hot mixing also spikes early heat, improves packing around aggregate, and consumes free water quickly, limiting later shrinkage cracking. Add the pozzolana. Volcanic ash isn't filler, it's a chemical partner. Mixed with lime, it builds calcium aluminum silicate hydrate, CaSH, a binding gel that is more complex than the CSH of most modern Portland cements, and can incorporate aluminum from the ash into its structure. That extra aluminum changes how the gel resists ion attack and slows dissolution in hostile environments. In marine placements, seawater isn't an enemy, it's part of the cure. Long-term reaction between seawater, volcanic particles, and lime clasts drives the growth of rare, crystalline phases, Al-tobermorite and related minerals, inside the concrete. Those crystals lock aggregate to matrix and strengthen interfaces that otherwise act like weak seams. Counterintuitively, wave action can feed the process. New crystals grow along pathways where water moves, tightening the microstructure over time. Now look at how Romans cast. They favored massive, low-water mixes rammed into formwork around large stone aggregate. Low water means fewer connected pores after hardening. Coarse aggregate provides a skeleton that limits shrinkage and spreads stress. Because there's no embedded steel in these giant blocks and domes, there's no hidden corrosion engine to blow apart the cover concrete from within. Modern reinforced concrete, by contrast, solves tension with steel but creates a new vulnerability. Chlorides and carbonations sneak in, corrosion rust expands, and the surrounding paste spalls outward. So when people say modern concrete crumbles, they're usually describing reinforced systems where the steel is the failure initiator under salt, moisture, and oxygen. Not that Portland cement is intrinsically incapable of lasting. Roman concretes also exploit graded density and smart architecture. The Pantheon's dome isn't one uniform mix. It steps down in density with lightweight volcanic pumice aggregates toward the crown while using heavier tuff below, cutting dead load where stresses are highest. The oculus removes material at the most critical zone and reduces thermal gradients. Masonry rings and hidden coffering act as ribs. Concrete is placed to work in compression, where it excels, not forced to carry tension it resents. At harbors, blocks were cast in place. Pozzolana lime mortar rammed with tuff or lava aggregates inside wooden boxes that sat partly in seawater. The early wet cure and steady ionic supply set the stage for that long mineral evolution toward tougher, more crystalline bonds. Zoom into the microstructure to see why cracks don't win. In a Portland system, microcracks can connect pores, bring in chlorides, carbon dioxide, or sulfates, and start a cycle of damage, especially once steel is present. In Roman matrices, hairline cracks often meet lime clasts or rims rich in reactive phases. Water dissolves a little calcium. The local pH and carbonate supply favor calcite precipitation that reseals the gap. Elsewhere, volcanic glass slowly yields silica and alumina that rearrange the CaSH gel. Along some long-lived marine interfaces, needle-like tobermorite and platy crystals fill space the way frost fills fissures. But instead of wedging things apart, they glue them together. Crucially, those processes are slow. Durability comes from reactions that don a T burn out in months, but migrate through the matrix for years, stabilizing rather than weakening it. The ingredients alone don't guarantee success. Placement and curing matter. Roman builders packed mixes with minimal bleed water, kept lifts shallow enough to ram thoroughly, and protected fresh placements from rapid drying. They also leaned on stonework to carry shape and stiffness, so the concrete didn't need to do every job by itself. Wall cores are a rubble and mortar composite where large stones carry load while mortar glues and redistributes stress. In domes and vaults, coffering and ring action mean loads flow around weak points rather than straight through them. What about strength versus durability? Modern Portland concretes can reach very high compressive strengths fast, which is gold for schedule-driven projects. Roman mixes don't chase early numbers, they chase stability. Their secret is not extreme strength on day 7. It's a microstructure that resists ion ingress, heals microcracks, and doesn't babysit corroding steel. Given time, they trade speed for longevity, especially in marine or damp settings that keep the chemistry alive. Could we copy this today? Parts of it, yes. Hot mixed lime pozzolan binders for non-reinforced elements, low water placement with careful compaction, and volcanic ash or engineered pozzolans to upgrade durability even in Portland systems. Self-healing ideas are already being explored in modern concretes. Capsules that release healing agents, bacteria that precipitate calcite, and supplementary cementitious materials that keep free calcium available for later crack sealing. But the biggest design pivot is strategic. Don T expect buried steel to survive aggressive exposure without heroic protection. Either separate the roles, use non-corroding reinforcement or pre-stressing systems with extreme cover control, or lean on compression-centric forms and non-reinforced mass where possible. If you adopt Roman chemistry without Roman structural logic, you only solve half the problem. Common myths are easy to clear. Romans had a single magic recipe. They tailored mixes by site and era. Marine concretes differ from dome cores and from wall mortars. Roman concrete is stronger than modern, apples and oranges. Portland mixes can be far stronger in compression, but many modern systems age poorly because of steel corrosion pathways and a different pore network. Volcanic ash alone is the secret. Pozzolana matters, but hot-mixed lime clasts and long-term mineral evolution are key to self-healing behavior. Seawater ruins concrete. For Roman marine concrete, it's a nutrient stream, slowly building binding minerals. For poorly protected reinforced concrete, it's a killer. If you want a field checklist for reading Roman concrete on camera, use 4 lenses. Matrix. Look for lime clasts and pozzolanic reaction rims. Interface. Check aggregate paste bonding. Marine blocks often show crystalline overgrowth along contacts. Pores and cracks. Are hairlines bridged by calcite or needle crystals rather than widened? Context. Is there steel? If not, you've removed the main 20th century failure mechanism. Tie shots of harbor blocks and Pantheon coffers back to those lenses, and your audience will see why Roman concrete is really a set of compatible choices across chemistry, placement, and structure, not a single ancient hack. To close, here asks the logic in one breath. Roman concrete lasts because it is a pozzolan lime composite mixed hot, packed dense, cured patiently, and used in forms that keep it in compression and away from rusting steel. Its lime clasts and volcanic glass continue reacting for ages, turning water ingress from a threat into a slow-motion repair kit. Modern concrete often fails early, not because it cannot be durable, but because we pair it with steel in harsh exposure and optimize for speed, not for mineral evolution. Blend the best of both, Pozzolans and hot lime concepts where appropriate, designs that minimize corrosion risk, and you can push service life far beyond the usual playbook. If this evidence-first breakdown helped stick around, we'll unpack the Pantheon graded density dome and a Roman harbor block under the microscope to show exactly how those lime clasts and late-grown crystals bridge cracks you can barely see.